Ladies and gentlemen, thank you all for coming on such a wet, grey evening. Hopefully the traffic will have subsided somewhat for those of you who are driving after the talk. And this evening I'm delighted to present Lou Ashwal to talk to us about hidden continents. But before he gives his presentation, as ever, I'd like to thank John Hancox of CCIC Coal for providing the drinks and chips. And we look forward to your talk, Lou.
Really? Are you ready?
I'm ready.
Great.
On your mark, get set.
Shut off the lights. Why does it feel... Anyway. Okay, folks. Thank you for coming. This talk I've given many times in lots of places around here and several countries around the world. I guess the latest one was 2 weeks ago at the SAGA meeting. SAGA is the geophysical group. And Judith, I guess, had an open spot this week and asked me last week if I would do this, and I said, sure, why not? So this talk is a collaboration of three people, me and my expertise. I'm a petrologist and I know about rocks and minerals and geochemistry a little bit. Michael Wiedenbeck, some of you know, he is an instrument guy and he operates this big fancy ion probe instrument in a place called Geoforschungszentrum, which is in Potsdam, Germany, just outside of Berlin. And then everyone knows Trond Torsvik. He's a guy who reconstructs continents and thinks about geodynamics and is a paleo-mag guy. And so it's three very diverse sets of expertise that came together to put this paper together, which is a sort of a provocative suggestion that we've had for a few years that says that there are pieces of continent scattered around the world in places where they shouldn't be, in places where we don't expect them. And specifically, this piece of work that I'm describing today is, our claim is that there's a piece of continent under the island of Mauritius, which is a very young oceanic hotspot-related volcano. So what the hell is a piece of continent doing under there? And that's what I'm going to explain to you. So this paper was published in Nature Communications a little over a year ago. It came out 31st January 2017. And the Nature group sometimes has an embargo on research papers in terms of the press coverage. And so they held the embargo until 4 p.m. Joburg time on that date, 31st January, and then it was opened up so the media could report, do whatever the hell they want. At 4:01 on that day, I remember this very clearly, my cell phone started to ring, my email started to go crazy, WhatsApp and all, you know, every way of communicating with me, including my desk phone, started to freak out. And it was all media people seeking interviews and wanting information. They wanted to interview me. And boy, I tell you, I remember, so this is a sampling of the coverage that this work has received. And I still to this day don't understand why, but there it is, you know. So there's about 25 media names here which covered this story, and there's about 200 more. So I just put a sampling of some of them. I mean, look at this. New York Times, they called me up. So the science reporter from the Times, when you get a phone call from the New York Times, you know that you've done something special, perhaps. I don't know, but I was very surprised. So Time, Newsweek, CNN, all the TV networks covered this story. Cosmopolitan magazine wrote a story in which my who would think that my name one day would appear in Cosmopolitan magazine? But sure enough, there it is. You know, and this was very interesting. So there was about a period of 2 weeks or a little more, maybe 3, in which I did interview after interview. I think I have about 50 interviews, some live, some recorded. I've been on TV several times, and some of them very interesting, and radio. So I remember being interviewed by Radio Bogota in Colombia. So this was a live interview that I did, and the questions were asked to me in Spanish, translated by somebody into English. Then I would give the answer in English, and it would be translated back into Spanish for the listeners. You know, and the interview, 7 minutes, no more. But when you have to do this translation thing, it takes a lot longer. But you know, eventually I got very good at doing this. And Sue Webb has a photograph that she posted of me downstairs. Some guy in Canada tricked me into doing a live TV interview in the middle of the night here. So it was about 2 a.m. and I did this interview with my cell phone as a camera, which was propped up on a box of wine, sitting on top of a bag of coffee beans and propped up with a tomato. And I did a 20-minute live TV interview for CBC in Toronto. The most amazing stuff. And I still don't know why this happened, but we can talk about what the possibilities are now. Interesting thing, you may have seen this thing. So the Wits University Public Relations Office came to me, interviewed me for 2 hours in my office, and then reduced it to a 4-minute video, which they have put on YouTube. And as of yesterday, 700,000 some odd YouTube views, which is a lot more than Lee Berger would ever dream to get on a YouTube video. You know, I really do have to assure you that I'm not the type of guy who is looking for this type of publicity and public attention and so on. But there it is. So these guys who did this video in my office, I remember while they were setting up their equipment, I had some time to kill, so I started singing a song, and the song I sang was Taylor Swift, Our Song. And I was just killing time, but those sneaky buggers recorded this. And they put my singing at the front and the back end of this video, which is now 700,000 views. So, you know, maybe that's why this media attention. I can tell you, I'm still waiting to get a phone call from Taylor Swift herself, and that has not happened yet. I made her more famous than she already is. But she didn't call me. So maybe I should have done a Katy Perry song. Next time. Okay, so there's that. So, you know, we can think about why this got such a media frenzy. And part of it is because most of the media coverage used the phrase a lost continent, which we specifically avoided using. Why? Because it brings to mind this idea of Atlantis, which was initiated by this very overrated man called Plato in 360 BC. And this is the perception that he wants you to think. So there's some sunken continent that we call Atlantis, and it looks like this maybe, but you know, that's not what we're talking about. So we wanted to avoid the idea of Atlantis, but nevertheless, all the media guys said, well, you know, you found Atlantis, so tell us all about it. So then I had to explain, no, this is not what it is. But look at all, Time magazine, CNN, even Cosmos said, scientists have discovered a lost continent at the bottom of the Indian Ocean, and they're calling it Mauritius, which is true. So Cosmo got a pretty good article. But Time and Newsweek, both of them botched this very badly. They misquoted me, they had misinformation, they made stuff up that is totally false. And so, you know, Trump talk about fake news, and he's right. neither Time nor Newsweek interviewed me. So, you know, you want to write a story that has some credibility, you talk to the person from which it comes. Anyway, so this is an interesting thing. I was watching CNN News one evening in my house, and there was an ad break, 30-second ad break, which was a travel ad, come to Mauritius, you know, and it had a pretty girl in a bikini and on the beach and so on, and you know, it's a beach resort paradise. But this is the last screenshot in that 30-second ad, and it says Mauritius, home to the lost continent Mauritia. And that comes from us. So it's fantastic stuff. So, you know, all this media coverage was very interesting. It was kind of fun and exciting, but I assure you, it really was exhausting because I didn't stop doing interviews day and night for a period of 2 weeks. So be careful about what you write in Nature. So, you know, some of these interviewers, and specifically, it was the guy from the New York Times, the science reporter for the Times. His name is Nicolas Lafleur. I got to know him pretty well. And he called me on the phone. He asked me, so when I was a little kid, he said, I was told that there are 7 continents. And they're the names of the 7 continents. And he said, are you telling us that you have now found number 8? And I said, no, just hang on a minute. This is not what we're talking. So I had to explain to him the different ways in which the word continent is used. So I quickly, somehow, was able to tell him that, you know, your perception of continents is the way a geography department thinks about continents. So what is a continent in their mind? So there are the names, North America, South America. You know what they are. So they're big places that sit up above the ocean so people can live on them. And, you know, so there's these names that you're forced to memorize as a school kid. But this is totally artificial and arbitrary, and it's quite silly. So I had to explain the difference in the way the word continent is used from a geographer to a geologist. You know, this geographic way is quite silly. Why is Europe considered a different continent to Asia? They're connected to each other, for God's sake. Is it because the people in Europe, oh no, we can't be linked with Asia because Asia has Chinese and Indian people. We don't want that, so we have to be separate from. There's big pieces of continent that are not elevated sufficiently to the status where you could. Greenland is a good example, but there's lots of other ones. Borneo, Madagascar. These are big places that are continental in our estimation, but they are not. They don't have the status of continent. India is referred to as a subcontinent. What the hell does that mean? You know, so I was able to explain to the New York Times that continent is not the way you think of it. In a scientific way, a continent is defined in terms of its thickness, its composition, its ages, and so on and so forth. And in fact, pieces of continent occur in all different sizes and shapes, from big ones to medium-sized ones to tiny ones. And what I'm saying is we have provided evidence that there's a little piece of continent under the island of Mauritius, which is over here somewhere. So he was able to write a pretty entertaining article for the Times about this distinction. How do we use the word continent? It was kind of fun. So, you know, then the next question is, okay, how, if you say a little piece of continent is under a volcanic island in the ocean at Mauritius, how did it get there? And the answer, you know, allows you to then discuss plate tectonics, and I don't need to explain that to this audience, but you know, so here's a summary picture of how plate tectonics works. I don't have to describe it in detail. I stuck this picture of Harry Hess in there for when I gave this talk at Princeton last year, because that's where he's from. And here's he's drawing a picture of plate tectonics on his blackboard. It's wonderful. So the idea is that that new crust forms at mid-ocean ridges. It's basaltic, and you have oceanic crust, and the continents ride as sort of passive passengers, and sometimes they collide together, Sometimes they reach a subduction zone and strange things happen to them. But the main point is that in the oceanic crust, there is no rock, there is no crust older than about 200 million. 250, no, I don't think so. I think 200 is about the maximum. Most of the oceanic crust is much younger than that. So we are going to provide evidence that there is a signature of old material at a place where it shouldn't be. So on top of plate tectonics, of course, the Earth, number 2, how the Earth works, part 2, is mantle plumes, blowtorches, stationary blowtorches that come from the very deep interior in the Earth, probably the core mantle boundary, and they are fixed with respect to plate motions that take place over them. And as you all know, they form a chain of islands with progressively increasing ages away from the active hotspot that we can look at today. So a good example is Hawaii. So here is the active blowtorch sitting under the island of Hawaii, 0 million years. And then the chain, the Hawaiian chain and the Emperor chain track the motion of the Pacific plate over the past 70 million years. It's fascinating to see that there is a bend in the oceanic chain of islands here at about 40 million years ago, which can only mean that the motion of the Pacific plate suddenly shifted from one direction to another. So that's pretty cool. So you know most of that stuff. So here we are in the Indian Ocean, and there's the island of Mauritius, and it's the same kind of story. So the active blowtorch, the hotspot, is presently at Reunion, and Mauritius is the second youngest island in a hotspot track that leads from Reunion all the way back 40 million years through this chain of islands to the Deccan at about 65 million years ago. So that's where the Reunion plume was, producing this huge outpouring of lava, the large igneous province of the Deccan, at 65 million, which is about the time that coincides with the demise of the dinosaurs. And there are some people who make a link between the formation of the Deccan large igneous province and the death of the dinosaurs. But there's also the impact crater that coincides in time with that. So it's an interesting story, but you know, our story relates to this chain of hotspot-related volcanoes, and it isn't quite as simple and linear as the Hawaiian chain because the beautiful linear track of hotspot islands has been disrupted by younger spreading ridges. And so it's a bit more complicated to visualize this in the Indian Ocean. But anyway, our story is about Mauritius, and here is the geology of Mauritius. Very simple. It's a small island, about 50 kilometers by about 40, so 2,000 square kilometers, and the geology is all basalt. So pretty simple to map. Those people who want to make a more detailed looking map than simply one color have divided the volcanics in Mauritius into 3 series, an older one, intermediate, and younger. But the main action is in the older. So between about 4.7 and 9 million years ago, it's this green stuff, and that is the big mountains that you see in Mauritius, which I'll discuss later. And then these 2 other colors, the intermediate and younger, so between 3.5 and about 30,000 years ago, it's peanuts in terms of volume. So you can think about this tan and light blue color as sort of a very thin coating of paint on the surface of Mauritius. So the volume here, the big stuff is these dark green, the big mountains. That's where most of the volume of the lava occurred, and the rest of it is almost nothing. So what becomes important to my story is that in addition to these basalts, there are 1, 2, 3, 4, 5 localities in which an unusual rock type called trachyte can be found. And I'll tell you a little bit about trachyte because that's where we found the evidence for the hidden continent. So the next picture. So this story that I'm about to tell you is, I feel it would be irresponsible if I didn't give you the background here. So It started in that year, 1999, with this guy, Bjorn Jamtvedt. Some of you know him, Norwegian guy. And he was he accompanied me and Trond and a master's student from UJ, then in those days it was called RAU. Her name is Lisa Carter, and we were going to India to do some geology in India for her master's. And so the travel agent who organized a plane ticket from Joburg to Mumbai, for some reason, I don't know why, had us on a 2-day stopover in Mauritius. Why this happened is just a fluke. So Bjorn said, well, instead of doing what we're supposed to do in Mauritius, which means go to the beach and go swimming and snorkeling and look at the pretty girls in bikinis and so on and so on, he said, I don't want to do that. Instead, let's rent a car, we drive around and we look at the rocks. It sounded good to me. So we did that. And he revealed that he wanted to collect a big sample of basalt to take back to Oslo to see if he could find zircon in there. And to this day, I don't know why he had this idea. But he did that. So we helped him get a basalt, he took it back to Oslo, and yes, he found zircon in there. Had the zircons dated. Those zircons turned out to be Permian, about 250 million. I think it's Permian, isn't it? 250? Yeah, something like that. Anyway, so he got really excited because there's no way that there should be a 250 million year old zircon in a basalt from an island where the maximum age is 9 million. So he got very excited. He wrote this up as a paper, submitted it to Nature. Luckily, the paper was rejected. Why? Because those zircons turned out to be contamination from the grinding and crushing equipment that he used in Oslo to process this piece of basalt. It makes perfect sense. I mean, if you know anything about the geology of Norway, what do you have in Oslo? The Oslo Rift, which is a huge bunch of magmatic rocks of Permian age. So obviously what happened was somebody had crushed up an Oslo Rift rock in those grinding machines. He came along with a Mauritian basalt, and little bits of those zircons contaminated the sample. And so, luckily, the paper never got published. But Bjorn, being a Norwegian, very stubborn guy, and he did not give up. 6 years later, he tricked 2 of his buddies, Ebba and Hans, into go back to Mauritius. He told them, go back to Mauritius and don't collect basalt. Instead, collect beach sand. And so these 2 guys collected beach sand from 2 locations. It doesn't really matter, but you know, the idea was if we get beach sand, then Mother Nature will be doing the work for us. We don't have to worry about contamination from grinding, crushing equipment. And so in order to avoid that, they used these plastic beach toys instead of metal shovels and hammers and stuff to do the collection. So they brought the stuff back to Norway, and sure enough, they found more zircon, which were analyzed. And now they produced 20 grains of zircon from these 2 sand samples, Precambrian, all Precambrian ages. And so Bjorn reinvigorated his excitement, and you know, it took a few years, but we got together and wrote this paper that was eventually published about Mauritia. So there was 2 pieces of information that we used. One was the presence of ancient zircons in a 9 million year old volcanic island, so 660 to 1971 million years. So old zircons, and then one of our colleagues called Nick Kuznir, geophysicist from Liverpool University, was able to produce this map, this image, which is a gravity map of the entire Indian Ocean, derived from satellite gravity data. And it's, you know, he processes the data in strange ways, making corrections of various kinds, which I don't need to bother going into. But basically, this image is a crustal thickness map. And so the areas that are red have high crustal thickness relative to the normal kind of thickness of oceanic crust and lithosphere that you expect in normal ocean basins. And so on that basis, we proposed that all of this red stuff is abnormally thick crust, and you can see that it extends down to Mauritius. So the idea was that there's a piece of continent under Mauritius, which we called Mauritia, and we published this paper in 2013, a Precambrian microcontinent in the Indian Ocean. First author was Trond, because he's always the first author. Me, I'm at the back end of this thing. I don't really care. So, so here is this paper, and we made this map suggesting that at some time in the past, and forget 750. So this could be a reconstruction. There's Madagascar, there's India, and we propose that there's this thing called Mauritia in between, which consists of a little piece of continent under Mauritius, and then these other places in the Indian Ocean which have thick crust that represent sort of a microcontinent or a continental fragment that we named Mauritia. We named it Mauritia to glorify Mauritius because that was the very welcome source of all the exciting stuff that we found. So Mauritia, we propose, consisted of a whole bunch of other little pieces of continent that underlie Mauritius and some of these other places that you won't have heard of because most of them are submerged, or they're blanketed by coral and other kind of bad stuff that you find in the ocean basins. So we proposed this thing, Mauritia. We got it published in Nature, but scientists, and I'm a very good example of what I'm about to tell you, scientists tend to be very critical and very skeptical and very grouchy. And so we received reviews and comments and emails from these grouchy scientists who said, how can you be sure that the zircons that you recovered from those beach sands in Mauritius, how do you know they weren't transported from somewhere else, like Madagascar? Transported by the wind or by ocean currents. And this was an interesting. In the reviews of our paper, one reviewer said, it's possible that a bird could be feeding in Madagascar, eat a zircon, fly to Mauritius, and then poop out the zircon in Mauritius. How do you know that? How can you prove that didn't happen? Could it be rafted on a piece of floating pumice from some other place in the ocean? Could it have been stuck to somebody's boots and they walked around the beach and it fell off of their boots, or tires from a vehicle or something? And the answer is we can't prove any of these things wrong. We can say it's unlikely. A bird flying 700 kilometers would have to remain constipated the whole way. And remember that this bird is flying against the prevailing wind, which is going the other way. Ocean currents are going the other way. It's very unlikely that wind or ocean currents or birds or any of these other things. But, skeptics are skeptics, so be that as it may. So, we left this alone for a while. We got our paper published, but Trond kind of encouraged me or induced me to go back to Mauritius with him for another project, which is irrelevant to the story. But during that experience in Mauritius, and I've now been there 5 times, so I think this was in 2013 or something, I can't remember. We were sampling all around the island, and by accident we came upon some of these trachyte things. And I became interested, for who knows what reason that I become interested in things, but I became interested in how did these trachytes form. And I'll tell you what trachyte is in a minute. I'll show you a picture. Well, here it is. Trachyte, alkali-rich volcanic rock, commonly showing alignment of alkali feldspar crystals by magmatic flow. So you find tiny little outcrops of these trachytes, and I became interested in figuring out the petrology and the so I did everything a person like me is supposed to do: thin sections, geochemical analyses, trace elements, major elements, minor elements, isotopes, microprobe analyses with the help of Peter. You see his name here somewhere, Peter. Peter helped me with the mic. So we wrote this paper in 2016, Journal of Petrology, proposing, and this is a very iconoclastic suggestion of mine, that the trachytes are not produced in the normal way that a petrologist would think, which is by fractional crystallization. Instead, I said, no, that ain't going to work for these rocks. Instead, I think they are direct partial melts of the mantle. But that story is a separate one. What's interesting and important here is the nature of the trachytes themselves. So here's a picture of me in 2014 looking at an outcrop of trachyte, and they're quite shitty rocks, I have to admit. Most of them are very weathered. They're crappy looking things. You can't see much from outcrops. What am I doing? I think I'm using a pencil magnet to see if the trachytes are magnetic, whatever. So here's what they look like in the microscope. So PPL, XPL. So you see these alkali feldspar crystals all lined up. This is typical of trachytes everywhere in the world. They're all lined up, alkali feldspar, a little bit of nepheline, a little bit of agerine and iron-rich CPX, and a little bit of zircon. So in doing all this geochemical and petrological work on the trachytes, it became apparent that they're full of zirconium. And zirconium, 800, 1500 ppm, that's a lot of zirconium, which should tell you that rock should have zircon. And sure enough, I was able to actually see it in thin sections. And so I said, well, why don't we take some of these trachytes, separate the zircons, and see if we can find old ages. That will eliminate these grouchy critical people who say it was transported by birds. By the way, last time I was in Mauritius to give this talk, I found a bird. And I asked the bird, it was a beautiful little orange jobby, and I said, did you eat a zircon in Madagascar and bring it here? And the bird did not answer me, which I think is very suspicious. So anyway, so if we can find zircon in a Mauritian trachyte, you eliminate all this problem of transporting zircons. And sure enough, so it says here, we recovered 13 grains from a single sample. It's this one, Mao 8. And I gave the sample to Michael Wiedenbeck in Potsdam and told him, please be careful to avoid contamination from the crushing and grinding thing that we had the first time. And so instead, he didn't use any kind of crushing. He ground this rock using a rolling pin, stainless steel rolling pin, which was a brand new one. And so it's not from contamination of a grinding machine in Potsdam. And incidentally, no rock of sufficient age to the zircon ages that we got has ever been processed through the lab in Potsdam. So how else could it have gotten in there except from the rock? Could it have been blown in the window? Did a birdie fly from, where would the nearest Archean rock to Potsdam be? I don't even know. Sharad, you know. Where's the nearest Archean rock to Potsdam? Finland. Yeah. So a birdie would have to fly from Finland. Anyway, so we think these are, so this is the instrumentation used, and you've seen this before. Sarah has shown lots of pictures of this. This is the ion probe instrument at Potsdam, basically similar to the instrument that you may be more familiar with called the Shrimp, that Richard Armstrong has been selling data from that instrument to us for years, but now we have access to this thing for free, so we're very happy. So you all know what this machine can do. So 13 zircon grains he recovered from one trachyte sample, and most of them, 10 of them, are young, boring, uninteresting. You can hear the pictures. These are the spots from the ion beam that's used to analyze the ages. So each one produces a very precise age. So the young grains are all featureless, boring, flat-looking things, and they give young ages between about 4.9, 6.2, average around 5.7. So this is the age of the trachyte, which makes perfect sense because the trachytes always occur with the older series of basalts in Mauritius. between 4 or something like that, 4 and 9 million. So that is not a surprise. 3 of the 13 grains caused all of this media excitement. So the 3 grains, between 50 and 100 microns across, yielded ages that were spectacular. Okay, so they're all Archean, 2.5 billion to 3 billion. Now, this result is completely unexpected and exciting, I guess. No other young oceanic volcanic rock has ever produced any grains or fragments or age information of that magnitude. So I'll show you what the concordia diagram. You know, the first prize that we were looking for, which we didn't find, unfortunately, would be a zircon grain that has an Archean core and a rim of 5 million years, which would prove that this zircon was a fragment in a young ocean volcanic rock. But we didn't find that. Nevertheless, we're confident that these zircons are not extraneous. So here's the concordia diagram. Kind of boring looking, I won't dwell on it, but so this is all the age information. So these red dots are the beach sand zircons, and these ellipses are the ion probe measurements from Michael Wiedenbeck. You see they go back almost to 3,000 million. So what we did was we plotted the age information on a histogram, so we get an age frequency spectrum, and then we can compare it to the age frequency spectrum of other places in the Indian Ocean, like Madagascar, which we show here, but I'll get to that in a minute. So the idea is that you only really need to look at this picture. So here is the plume coming up into the oceanic lithosphere, producing the Mauritius volcano, and the source of the trachyte is down here in the plume somewhere, and it produces a magma that comes through the lithosphere and must have picked up some zircons from a fragment of continent that lie under the volcano. It can really mean nothing else. I can't think of any other way to explain this. It can only have come from continental crust. So we suggest at 9 million years ago, or 6, a fragment of ancient continent, by coincidence, by chance, happened to be sitting at a place where the Mauritian volcano started to erupt. And then the continental fragment was then blanketed by these basaltic lavas, and at 6 million years ago, the trachyte picked up a piece of zircon from this ancient fragment of continent. So, you know, a lot of the media asks me, well, how the hell can this happen? You know, and then you have to begin explaining it in terms of Gondwana and continental breakup and fragmentation of continents and so on. And so I show this picture to illustrate this point to the sort of public audiences that want to listen to this talk. And I show a movie, I commonly show a movie of Gondwana breakup. You've all seen this before, but I'm prepared to show it to you again. Do you want me to do that, or should I just bypass it? Huh? Show it. Okay, so Grant showed me how to do this, but the screen is now dead. D-E-A-D. Huh? You should use the mouse. The mouse is ineffective in this thing here. So what am I trying to do? Minimize this, right? And then go here. And so here is a movie, a little animation produced by Colin Reeves about 20 years ago. So this is nothing new. You've seen this before. So I'll run this movie. So this is Gondwana at 200 million years ago. And you know, it's kind of cool to imagine that, that all across Gondwana 200 million years ago, dinosaurs would have been roaming around happy and doing whatever the hell dinosaurs do. So let me make this go here. It's this way, right? So now Gondwana is going to break apart. So our story, you know, in the Mauritius, it speaks about how continents break apart, the details of that process, and of course the reverse of that, how we can fit them back together. So this is Gondwana. The red things are the big lava. So that's the Karoo. India decides to take off at about 60 million years ago, and breaks the speed limit, shoots through the Indian Ocean, crashes into Asia to produce the Himalayas. And so here is the present-day Indian Ocean developing, and our thing is situated somewhere between Madagascar and India, and where it would have been reconstructed during the breakup time. And so this movie illustrates a rather simple story of continental breakup, supercontinental breakup. That's familiar to most of us, but our work, mouse, maximize, and then push this damn thing, and go back to the talk, right? So, one of the implications of our work is that continental breakup is not as simple and clean a process as was illustrated in the movie and maybe perceived of by most people, but instead it's much more messy, much more complicated. And when continents break apart, it's possible that they leave little fragments of continent in various ways, in various places, littered throughout the ocean. So that's kind of the main message of what we're saying. And you could ask, well, how is it that, Madagascar breaking away from, how could it leave a little piece of stuff that would then be blanketed by more? How could it leave that behind? And the answer is a well-known process in plate tectonics called mid-ocean ridge relocation, or ridge jumps. So I illustrate in this panel here. So here's two continents breaking apart. There's a new ocean forming. RA stands for active ridge. And then there's a plume that decides to impinge upon the lithosphere. And it could happen anywhere. But the ridge sometimes will feel that, detect this, and it will say, you know what, I am not happy spreading over here. I'm going to jump over here. And so here is the ridge, and then at this time, it changes to ER, that's extinct ridge, and it begins spreading near or at the location of the plume. And so these mid-ocean ridge relocation events happen frequently in the history of plate tectonics that we can detect. And so in fact, in the history of Gondwana breakup leading to Mauritius, there have been 4 ridge jumps that have left little pieces of microcontinent littered all over the place in the Indian Ocean. And so that's one of the ways people think that microcontinents or continental fragments form. There's other ways, but we don't really have to get into the details of this. And so here is the present-day Indian Ocean, and here is Mauritius, where we think we have detected a piece of continent underlying the volcano. But then there are these other places where we propose there's also continental crust. So some of them you know, some of them you don't. Nazareth Banks, that place I never heard of. Chagos, the Lacadives, some of these other places. The Seychelles is a good example of where we know for certain that there's a piece of microcontinent there, because there's Precambrian rock exposed at the surface in the Seychelles. So these are the various components of what we called Mauritius, and at some time in the past they were joined together to form this microcontinent that we call Mauritius. So this is our latest reconstruction of Mauritius. So it's more detailed than the previous one that we published earlier. And so, you could ask the question, okay, if you think there's Mauritius here between Madagascar and India, can you correlate it with anything that's known in the Indian Ocean? And really there are 3 choices. So here's the present day. Mauritius is there. So the 3 possibilities for a continent that could correlate with what we found in the zircon spectrum in Mauritius. So it could be Madagascar, it could be Seychelles, it could be India. Really, those are the 3 big ones. So you could start looking at the properties of these places. Seychelles is not going to work. Seychelles is unlikely because there's nothing older than about 750. There's no Archean rock in the Seychelles. You can exclude that. India is much more promising because there's plenty of Archean rock. But what India lacks is the Neoproterozoic signature. So you don't have very much in the way of 1,900,000,000 rocks in southern India, or anywhere in India really. But Madagascar is the best match because you have everything that you need there. And in this region of Madagascar, and in fact I think I have a picture of it in the next slide, yeah. So here's a blow-up of some region in Madagascar where we have overlaid the outline of Mauritius at the right scale. And here, from this region, you could extract all of the zircon ages that we found in the Mauritius trachyte and the beach sands. So here's an age frequency spectrum that we use to say, well, the most likely provenance of this piece of microcontinent under Mauritius is probably Madagascar. So it has that affinity. What does it imply? I said this already, not a clean breakup. So here's a series of time slices that Tron put together. We don't need to look at the detail, but the point is it's complicated, it's complex. It's not a clean, simple breakup story. There's ridge jumps and, here's one interesting, so 83, so here at 60 million years ago, this little yellow thing is the Seychelles. And you can see that it is sitting on the Indian plate. So this is the ridge separating the Indian plate, dark gray, from the African plate in light gray. So Seychelles on the Indian plate, at 56 million, the ridge has jumped and it's now transferred to the African plate. So you can take these little pieces of continent, various sizes and shapes, transfer them between different oceanic plates, leave them stranded behind in various complicated ways. So this complicated mess here, I really would like Tron to make a movie of this to illustrate better what we think is happening there. But doing these kind of movies is not so easy, and I can't really blame him. So, what does this imply? So a lot of these press people ask me, okay, so you found a new continent, big deal. Why is this so exciting? How can I make the story interesting to my readers or my listeners or whatever? And I didn't call you, you called me, So I had to quickly think of some implications. So I came up with one idea really quickly. It's sort of obvious. So imagine, so here's Madagascar at 90 million years ago, stuck up against Mauritius. So Madagascar, India, with Mauritius in between. Let's suppose you own a gold mine in Madagascar, somewhere over here, and it's a really good gold mine, and you're making a lot of money, and you want to explore for another one. If you're clued up, at least in some kind of way, about tectonics and continental reconstructions, you could say, well, let me jump over to India and look for another gold mine in terrain that resembles the one that my gold mine is in. And that's a good idea, and I'm sure that a lot of exploration companies have done this kind of thing. But our work shows that it ain't going to be so simple, because Mauritius has to have been in between. And Mauritius is now fragmented into tiny little things that are barely recognizable. And so, this idea of using plate reconstructions as an exploration tool is a good idea, but it's more complicated than we thought. So that satisfied a lot of the press. Other implications, a lot of people, including a lot of my friends, Martin de Wit was big into this at one time in his life. Noticing the straight coastline of Madagascar and the straight coastline of India, he tried to fit them back together, and then tried to match the geology across, so using big shear zones that occur in both. So, you could get a more precise reconstruction. And it really didn't work very well. It wasn't very convincing. A lot of other people tried it too. And the reason is because they didn't know that there was something else in between. So that explains part of the problem. Now, some of the press people said, okay, we get this. You found a new continent, little tiny thing, big deal. I get this exploration story, but really, how is a tourist, or how is a person who lives in how are they going to relate to this? The thing you found is under the volcano, We don't know how big it is. We don't know how deep it is. We don't know how thick it is. We can't tell. But nevertheless, if you're a tourist or you know, a person in Mauritius, you can't touch it, you can't walk on it, you can't see it, so who cares? Why is your story important? So once again, I had to come up with something that might be relevant. And so what I did was, I made a comparison between the elevation in Mauritius to the elevation of other hotspot-related islands. So, for example, in the Hawaiian chain. So here's Hawaii, that's the plume right now. And here at 10 million years ago is the island, which now looks like this. It's about the same age as Mauritius is from the present-day hotspot of Mauritius. So Mauritius, 9 million years old, has an elevation of over 800 meters. In the Hawaiian chain, the island that's about the same age has an elevation of 38 meters. So why doesn't Mauritius look like this? Instead, there's huge mountains there. So I thought, well, is it possible that Mauritius is elevated, has a high elevation, because there's a piece of continent under there that's buoyant and it's pushing it up? This is probably wrong. But it's something that you could tell a newspaper reporter, and they could, you know, they could get excited about it. And I'm going to tell you why it's wrong, and the reason that it's so you can make a plot of elevation versus the age of the. So here would be the active hotspot. So the black line is Hawaii, and the red dots are the Reunion hotspot and its chain. So Hawaii, the active volcano, 4 kilometers high. Reunion is 3 kilometers high. And then in Hawaii, you could look at the elevations as a function of time and distance away from the hotspot, and you produce this curve. Now, Mauritius does not lie on that curve, but I do admit that I only have 3 red data points. So it's not a fair comparison. But you could say that the elevation of Mauritius is anomalous, but it ain't fair to do that. It's irresponsible. The reason it's irresponsible is because there are a lot of other things besides the age of the volcano that influences elevation of ocean islands. And one really important one is plate speed. So the Pacific plate, we know, is traveling twice as fast as the Indian plate. Therefore, it brings the stuff away from the active hotspot faster. And so it's irresponsible to make a direct comparison between the two, and I admit that. So there's lots of other things. So here are a list of things I put together. What controls elevation of oceanic islands? You know, and we can look at all these things, and you know, and it's probably not true, but maybe it is. Who knows? So you know, there's the elevation story we could talk about, and then we could talk about this in geophysical terms. Now, I can tell you that a series of geophysics groups have done a lot of work in the Indian Ocean with deployment of a lot of seismic stations quite recently. And those guys do not like this story. They cannot see a piece of continent under Mauritius. Instead, what they see, instead of a sharp moho, that maybe is what you would expect, they see a transitional moho under Mauritius. At least that's what they tell me. Now, I am no good at all at seismology or interpreting receiver functions or anything like that. And so, you know, I believe that what they have is right. Instead, they interpret the structure of the oceanic lithosphere below Mauritius in terms of a variable amount of underplating of basaltic, gabbroic lavas and so on. And so what you have is a transitional moho rather than a sharp one. I'm not sure, but you know, when a geophysicist tells me what you suggest is not possible, I'm not worried at all. I've had this many times in my career where I can prove that their denial is equally as irresponsible. So anyway, I'm almost at the end here. You know, we could ask the question, okay, so if you believe this story, if you buy into, I'm telling you that there's a piece of little continent under Mauritius, is there anywhere else on planet Earth where we could find similar things? And the answer you know, there's some evidence, and there's also some places where we might want to look. So where else could we look for hidden? Well, one is Iceland. And Iceland is a place where we have published a paper, can't read the year, 2011, whatever the hell it is, that under Iceland is another piece of continental crust. And the lines of evidence were very similar. Old zircons, Precambrian zircons in Iceland, shouldn't be there. No rock in Iceland older than about 30 million or 36. And geophysical anomaly. And also there's a signature in the Icelandic lavas that can be interpreted in terms of contamination with having passed through continents. So we have this paper where we suggest that under Iceland, the Jan Mayen microcontinent, which is up off to the northeast, extends for some distance under the eastern part of Iceland. Okay, that's very interesting and exciting. Where else? So I think it was Alfred Kroner and his people who found old zircons in the Galapagos quite recently. Unpublished, only in abstract form at the IGC meeting in Cape Town, which someone pointed out to me after the talk was given, so I didn't hear it. But sure enough, they claim that there's Archean zircons in Galapagos. Okay, I don't have a problem. It could be a piece of South America under the plume-related Galapagos. And then there's a couple of other places in the mid-Atlantic. So at the mid-Atlantic ridge, people have found old zircons in dredge samples and I don't know what else. But you know, all of these studies are going to have to go through the same gauntlet that we went through. How do you know? How can you be sure that these are not contaminants from your crushing equipment, for God's sake? So, you know, you want to do this kind of work, you have to face that kind of criticism. And I'm not sure I have the energy to do this anymore, but, you know, some other places which are promising places to look are the Canary Islands, the Cape Verde Islands, very close to Africa, young plume-related volcanic islands. Maybe there's pieces, at least it's worth a look. Take some pieces of the lavas in these places and be careful and extract some zircon, see if you find anything interesting in there. I was recently in the Canary Islands for Tron's 60th birthday party, and I was prepared to collect a big sample of basalt from Tenerife, bring it back here and look for zircons. But when I got there, they said, don't even think about taking a rock sample off of Tenerife. This is prohibited unless you have a permit, which takes you 2 years to get. And if you try to take a sample of basalt in your luggage, they will find it in the airport and they will nail you and you'll be in big trouble. So I couldn't do that experiment. So you want to go and look in Cape Verde or the Canary Islands, be my guest. Interestingly, I think it was 2 weeks after our paper was published in Nature, this thing came out in GSA Today, 2017, by a group from New Zealand led by this guy called Mortimer. And he proposed that there is a big piece of continent, which includes where New Zealand is. New Zealand is there, but he thinks this whole thing is continental crust that is now submerged under the Western Pacific Ocean. And so when this thing appeared, the guy from the New York Times called me back and he said, well, what are you talking about? You have a tiny little thing you can't even see in Mauritius, and this New Zealand guy has this huge thing, which he can't see either, by the way, but you know, he wanted my comments, and so I said, oh my God. So I had to go and read this paper, and I made a comment. You know, I was not critical. I think he's probably right, but you know, it disturbs him a little bit that an object that big, why would it be submerged if it's continent? So his story is that, well, when you break apart continents, very often what you do is you stretch them and you thin them. So the idea is that it's submerged because the thickness is quite low, maybe 10 kilometers instead of 30 or 40. And I'm no expert on stretching of continents, but you know, it doesn't seem likely to me that you could stretch a piece of continent to that extent, such that it would be submerged. But maybe, I'm not going to say it's impossible. So anyway, here is my summary. I don't need to go through this. We found old zircons. We think there's a fragment, we call it Marisha. It matches Madagascar. It allows us to understand breakup and reconstructions better, maybe a correlation tool. Here's a good one. It supports my idea about the trachytes, that they come from the mantle instead of representing fractional crystallization. Because how else could a piece of zircon come into a trachyte unless it was derived from below whatever it picked it up from? So the trachytes are obviously subcontinental in their derivation. And so I'm happy that I was able to do it. So maybe there's some story with the elevation. There's other places, and that pretty much is the end. So on behalf of my colleagues here, Trond and Michael, I thank you for listening, and I thank Judith for inviting me to give this. So this picture is Trond and me, picture taken by Sue in some resort, holiday beach 5-star hotel. We're enjoying some fancy cocktails here, doing this work collecting trachytes. So that's the end of my talk, and I thank you very much. And I guess I now have to answer questions, which I'm prepared to do.
Well, everybody knows where to find Lou, so if you've got major discussions that you want, I'm sure he'd be happy to discuss with you. But let's take just a couple of short questions now, if there are some. Sharad.
That is my name.
Enjoyed the talk.
Short question, Sharad.
You mentioned that there are other fragments, such as perhaps the Cape Verde Islands, that may be floored by continental crust. Now, we currently, I'm supervising, together with this man here, an honest project that is based in the Cape Verde Islands, and we are testing another hypothesis, that perhaps there are zircons that which blew over from a continent. That's one of the criticisms that you had for your earlier nature paper. So now, if you suggested that there might even be a piece of continent underneath, and we have actually found zircons in beach sediments from the Cape Verde Islands, which are also volcanic and mafic, right? So how would we test whether those things have come from a continent or from a continent below the island?
The answer to you should be obvious. You don't collect samples from the beach. You look in the rock. So if there's a piece of continent under the Cape Verde, collect a piece of basalt or whatever the hell you like and see if you find zircon in there. But please be careful when you do the...
I don't have any basalt. I'm not testing that hypothesis.
Oh, okay. It's not... I don't have a problem that zircon can be blown from somewhere else and end up in Cape Verde. I think you would want to suggest that it comes all the way from North America, isn't it? No. Or is it from Africa? Huh? From North Africa. It's not far away. So sure, you could blow some zircon. But remember, zircon is a heavy damn mineral. It's not going to like to fly, and it ain't going to like to swim. So, I don't have a problem.
Robert?
Just a quick comment. You said your old zircons would confirm mantle origin for the trachytes.
Yeah.
Well, you can still have a mantle-derived melt passing through the continent and then fractionally crystalline.
Yeah, I suppose. Yeah. Yeah, what you say is possible, but then we would expect...
It's not really contradiction.
It's not a contradiction. My story is supportive, but not demonstrative. But you'd expect, in your case, to find zircon in the basalts. And I'm not sure.
One more question.
Very interesting. So your story has actually big implications for the Mantle Zoo.
For?
The Mantle Zoo.
The Mantle Zoo.
Like people thinking they work with uncontaminated basalts and thinking they pick up deep stuff like the
Absolutely.
If it sits essentially 5 kilometers beneath the island.
Absolutely. This becomes clear in Iceland. People, geochemists, very prominent, famous geochemists, love to use isotopes and all kind of fancy things in ocean island basalts because their perception is that we are away from the continents and we avoid contaminating effects. And so you know, Hawaii, Mauritius, and Reunion, all these. But if it's going through continent, then it's possible for it to inherit something from.
Iceland is even worse
And-
because Iceland is used as a model for alkene crust formation, assuming that sort of an oceanic plateau that forms now, that all the geochemical signatures actually come from alkene rock sediments.
Yeah.
So it becomes extremely circular.
Yeah, we have taken some of the basalts from this region in eastern Iceland and shown that you can explain their isotopic signatures with a contaminating component from Jan Mayen granite.
Lou, thank you. I'm going to stop the questions there. And next week's Geotalk is Berta Smith from UJ. And we have talks up until the end of May now. So please continue to support the talks. Thank you for those who've come from outside, from UJ in particular. And we look forward to you joining us for more talks as well. So, Lou, thank you very much indeed.